Today we have an IRIS-HEP Topical meeting about extending JAX with CUDA, and here to talk with us today is Dan Foreman-Mackey. And for those of you who don't know, Dan is an associate research scientist at the Flatiron Institute Center for Computational Astrophysics. But if you don't know him, you might be aware of some of his prodigious code contributions. He's very well known for in the MC world, not only for the MC Python library, but also for work on things like Exoplanet, and something that I use on a regular basis is Corner. Um, we invited him today because we saw him post a really interesting summary, as well as a study on extending JAX with both C++ and CUDA. So given that, we're going to let him take it away.
Alrighty, thanks so much, Matthew. So yeah, thanks so much for having me. It's fun to be here talking about something so niche. I organized this to be like pretty informal. So I have some slides that I wanted to go through at the beginning, sort of giving some context about like where I'm coming from and things like that. But really, I guess I don't really know too much about what everyone's backgrounds and interests are. So it sort of would be, I'd love to hear questions and discussion and things like that. So just interrupt me and that kind of stuff. I'm gonna start sharing my screen here to get started. Okay, so the topic here is extending JAX with C++ and CUDA. And I want to sort of start by saying that I don't really know very much about JAX, and my CUDA coding skills are pretty pathetic. My C++ is maybe a little better, but poor compared to others in the room. So, with all of those caveats, I clearly don't really know what I'm talking about, but one of my, pandemic focuses of my research has been on infrastructure and things like that related to scientific coding. And so I think there are perhaps some things that I've learned that will be useful. So I wanted to share some of those things. I wanted to start by putting up my contact information and stuff like that. And I'd love to chat more about these things if people have any, if any of these topics are of interest. Okay, so like Matthew mentioned, the reason specifically why I'm here is because I wrote this blog post that turned into a GitHub repository that's thousands and thousands of words about this particular topic, and I'm not gonna go as much into the technical details as I do on that post, and so check that out if you sort of for more details, but we can talk more about that later. Good. So I want to start with sort of a very high level context about sort of who I am and how I came to this particular topic, and like some of the motivating problems that lead me to think about using JAX, and in particular extending JAX with custom ops. I'll define all of that in a minute. So I'm an astronomer, and like a lot of physics, what we want to do is we want to collect some data and figure out what it tells us about physics. And in one way of doing that would be to write down a likelihood function and do some sort of numerical inference using that. And in astronomy, a lot of the time that's done with Markov chain Monte Carlo. And many years ago, I wrote this library, MC, which is commonly used in astronomy as a tool for doing MC. And sort of the key API decision in this code was that the way that you would implement your models was very much as a black box. And that so even though it's a Python library, the interface is just a function that takes a vector, a parameter vector, and then the user is required to return the log probability. And that's the entire interface. And that's useful within astronomy because a lot of the time in astronomy, we're trying to do inference with physical models that that are implemented as sort of, handed down old Fortran code or something like that. And there's sort of often a long history with how to evaluate these models. And so this kind of interface was pretty useful. So sort of as, I also used this library quite a bit, and I've spent a lot of time, sort of an embarrassing amount of time writing these Python libraries for model building. And I think this is probably something that a lot of people on this call also have experience with, sort of, kludging together models and sort of custom implementations. And so this was sort of for many years a big focus of my research program. And so one thing that sort of more recently I've been finding is that MC isn't necessarily the best library to solve the kinds of problems that I want to work on. And part of that is because if you have a large model with a high dimensional model, it actually is very inefficient. It can, it works well for, a dozen parameters, but once you get to ambitious models, like the kinds that I'm very interested in these days, it doesn't work so well. We'd rather something be a little bit, scale better. And in particular, as many people here will know, one way that you might do that is by using gradient-based methods. And so what I mean when I say that is, sort of Hamiltonian Monte Carlo classes of methods or variational inference methods, things like that. And the key point there is that, we had this likelihood function that I was talking about, and when I say gradient-based methods, what I want to do is I want to be able to take this derivative, the derivative of the likelihood function with respect to the physical parameters. And so this, this is, in general quite tricky. And in particular, even if I go through and figure out what all of those derivatives are, if I like change the parameterization or want to try to switch things around, that the bookkeeping gets to be a pain. And so, yeah, don't want to do that. But it turns out that there are lots of other platforms that might be useful for doing this kind of thing. In particular, there's all sorts of things like this, which despite the marketing, is not just a machine learning platform. It is also a model building framework. And so TensorFlow is one example. Another is PyTorch, things like Stan, JAX, which is the topic of today's discussion. All of these things are examples of model building frameworks where that are specifically designed to solve the type of problem that I was having, where I want to be able to efficiently compute models and their derivatives and be able to reparameterize and stuff like that. Good. And so the idea is that I want to be able to use something like this to do my data analysis in astronomy. I want to be able to use these tools. And so recently, sort of a class of or sort of a group of projects that I've been working on fall under this exoplanet umbrella. And so exoplanets is the field that I work in. But I also managed to get pip install exoplanet. And so I had to take it. And so there's a set of projects that live within this. And this is what the documentation page looks like for it. And basically the idea here was that I wanted to build a set of tools that would make it easier for exoplanet astronomers to use these existing model building frameworks. And in particular, I wanted to support the kinds of like custom physical models that exoplanet astronomers in particular want to use. And so I built this library on top of PyMC3, which you might be familiar with. And in particular, sort of more important for my purposes, PyMC3 is built on top of something called Theano, which is sort of the old school model building framework that is sort of it does a lot of the things that I was talking about that we want. And so I spent a lot of time figuring out how to implement the custom astronomical models inside of Theano. And so that's where a lot of my experience comes from. And so that's some context. Now, Theano, you might know, was discontinued many years ago, and the development was, and the PyMC developers took over the maintenance of that library. And just a few months ago, there was an announcement that essentially the development of Theano was getting reinvigorated. And one of the ways that was happening is that it was becoming more tightly coupled to JAX. So they had decided to support translating Theano graphs into JAX models. And so this meant that I had to start learning about how to implement things in JAX and figure out this connection between these two. This was exciting for me because it wasn't obvious exactly what the future was going to look like for these kinds of tools for the PyMC ecosystem. But yes, this is how I came to JAX essentially. A piece of trivia. I think that there's a nice post, by the way, Kyle says.
Yeah, I'm just saying that this article I think is worth a read, even if you're not really wanting to do specifically that. It's just it's a lot of interesting, thought-provoking stuff in there.
Yeah, absolutely. Yeah, and feel free to comment in the chat. I can see it here if you have any questions or comments as we go. Good. Oh, and then a piece of trivia I was going to say is that actually Theano has just been renamed to this, which I don't actually know how to pronounce, but and basically the idea is that there's one minor tradition that this is the daughter of Theano, and so this is the new name, Acera maybe, for Theano. Anyways, that's neither here nor there. And so now what I want to talk about is some motivation for what I mean by custom ops and why you might want to write them. And I think there's sort of a clear answer here. So essentially the question is, so there are these model building languages and you can specify your entire model in one of these high level languages. But sometimes sometimes you might not want to do that. You might not want to specify the full model in the high level language that you interface from Python, for example. And some of the reasons why are perhaps performance. So you might have a highly tuned C++ or CUDA implementation of the model that you want to use that's been tested over the years by by the community, and you can get much better performance out of that than something that's implemented in this more general purpose framework. And that's the main, that's sort of the main motivation for my purposes. But then another one is legacy, and what I mean here is that is specifically about the like history of the methods. So there might have, like maybe you have some quite complicated model, and there's been a huge amount of work like testing it and testing the edge cases and that kind of stuff, and maybe it's just a pain to like completely re-implement that inside of a new framework. And so being able to expose that well-tested implementation, might be worth it. And so that might be another reason, even if the performance isn't necessarily better. That might be a reason why you want to do this. But the sort of key point here, and one of the things I mentioned is that in astronomy, a lot of the time what we're working with are these, sort of like black box kinds of models that are, implemented in like Fortran 66 or something like that have been handed down through generations of advisors. And it's not obvious. I don't have an answer here for how to deal with something like that. And in particular, that's because the things I'm going to talk about here, it is actually somewhat tricky to tie it into the automatic differentiation framework. So when you have a custom op, like I'm going to talk about, you also have to be able to provide the derivatives, or some specification of how to propagate derivatives through your function. And so if you have some very complicated model, the details that I'm going to describe here are not going to just like immediately solve your problems. And so sometimes your life might be better just trying to re-implement it inside of one of these frameworks rather than trying to expose it this way. But I think that it's not, anyways, we'll talk more about that. Okay, so I wanted to give one motivating example. So here is like, this is the example that I wrote about in the blog post, and this is like, one of the core functions inside of an exoplanet astronomer's toolbox, and that's that you want to solve Kepler's equation given some mean anomaly m and eccentricity little e. You want to solve for the eccentric anomaly in this equation right here, and so you have to do that numerically, and there's like an insane literature, even papers coming out this year of better and better and faster, more accurate ways of solving this. And so there's a huge literature about this, and a lot of those methods are sort of very specific, very fine-tuning kind of points at the sea level that would be hard to propagate directly to something like JAX at a high level. Or they're iterative methods, which also don't necessarily translate so well for reasons that we can talk about some more. Now, this is a very small thing. Like this, this is a pretty simple operation. You have two inputs and one output, and it sort of has nice shapes and that kind of stuff, which is one reason why why this is a nice test case. Now, in practice, when I'm building my exoplanet model, there's sort of lots more pieces that go around this. Like this isn't my full model, and so my strategy for integrating with these libraries is to write a very small custom op that just evaluates, just solves this in C++, and provides the custom gradients just for that piece, and then it ties in well into the rest of the stack. In fact, I take it one step further, and I actually I fuse the next op that I always want to do into this one to get better performance. But in my production code, but for the purposes here, I think the key point that I want to make is that you sort of want to identify the smallest piece that you can provide custom, and then try to keep the rest of your implementation in the high level framework. And so that's the strategy that I would take for this. There's some questions about whether or not this is a good idea. You know, and in particular, you might want to actually benchmark some you know, and see whether or not this matters. I've found for this particular use case, this does tend to matter, because, you know, a single model evaluation, I might have to solve that equation, you know, hundreds of millions of times. And so any small performance increase there can make a huge difference to the computational efficiency of my code. But perhaps in a different context, it wouldn't make as much of a difference. And so, good. And then I don't know why I was going to say that, but anyways, let's just skip that. Okay, so now I wanted to talk briefly about the important parts of how JAX works, and this is where we're starting to get more technical. And I wanted to emphasize what I said earlier, is that I don't like my perspective on how JAX works is very much a user perspective. There's a lot of magic that goes on in there, and I will almost certainly say wrong things. So don't, you know, so interpret what I say accordingly. Good. So essentially, in all of these model building frameworks, like TensorFlow, PyTorch, JAX, Theano, what have you, there are essentially two key components, and they all approach them in slightly different ways, but a lot of the intuition is the same. So there's some first step where you somehow describe the relationship between your variables. And then there's a second step where you differentiate through that model. And like I said, there's sort of all of these libraries have a similar, but all do this. But JAX takes a fairly interesting approach to both of these. And so the like key words in JAX language are XLA for the graph building and autograd for the differentiation. And in fact, this is backwards. So JAX stands for, I think, JAX is autograd and XLA. So even the name emphasizes that these are the key components. And so XLA is a sort of it's the low level computation engine. So it does it is implemented in C++ and CUDA, and it exposes the fast linear algebra and all those kinds of things that you'd want for models like this. And then the autograd part is the higher level method for reasoning about derivatives and propagating forward and backward derivatives. And I'm not really going to talk about the autograd part too much here. I'm happy to chat more afterwards. We're mostly going to talk about the XLA part because that's what's relevant for the topic of today's discussion. Good. So I wanted to start by talking about how JAX does this graph building stage, because it's pretty fun. So here's a very simple JAX program here, and if we look, if we execute this function and look at what the x variable is when we call that function, it'll and here I'm passing in an actual NumPy array. What you would find is that when this function is called, x is a NumPy array with that particular with those particular values. So calling this function does what you would expect from a Python function. Now, if we then decorate this function with the JIT operator, which is the just-in-time compilation of these functions, which is the thing that makes JAX fast, we would find that if we inspected the value of X when it's called, instead of being a NumPy array, it's now this weird thing called a traced shape array, float 32, 2. And so what's happening there is that JAX is executing the Python function, but it's not calling it with a value. It's calling it with this abstract object that's keeping track of what the relationship is between different variables. And so that's cool because it lets you write something that looks a lot like Python without having to think about the graph in the same way that you do in sort of old school TensorFlow or Theano. But it has a nice way of what is called is tracing that function in order to like keep track of how everything fits together. And so the key thing here is that when the Python function is executed, the only thing that it knows about is the shape and type of the inputs, not the actual values of those inputs. And then in the back end, it knows how to run that through XLA with the concrete values. But when the Python is executed, it doesn't know about the values. And so one of the things that's cool is that if you call this function multiple times with arrays of the same type and shape, it will only execute the Python once. And so that's cool. And that's important for what we're going to do. Okay, and then the other thing I was going to say is that things get really funky if you then try to, take the derivatives of this. And there, some of the parameters have values and some of them are abstract, and all of that would become important when you want to actually implement the derivative rules here. But all this to say that the Python function can be executed several times with sort of very different types for the input parameters, depending on what you're doing with that function. Okay, good. So one of the things about this JIT compilation is that it can be super fast. So like it's quite impressive what it can do, because it's, after it runs the Python once, it doesn't go to Python anymore. It's translated everything into XLA operations. So in the background, it is just sticking in C++ or in CUDA and executing your full model, and everything's been connected together. And so that can be great. And I think, I've had a few cases where my intuition about what would be fast and what wouldn't wasn't necessarily true. And so it's quite impressive. But there are cases where this isn't true. And so if you're in that kind of situation, providing a custom op can be worthwhile. So I wanted to give a little, I don't know, pop quiz or something of an example of control flow, because this is something that can be confusing when you're first coming to this. And so here I have a Python conditional, which sort of at some level, JAX can support. But in fact, this function won't work right here. And the reason why is because the conditional is on this X value, which will have an abstract type when you pass it in. So this is no good. This you definitely don't want to do something like this right here. But something that you could do is this, where the abstract value does know about its shape. So you can condition on the shape and do control flow based on the shape. So you could do for loops and things like that as long as you aren't using the value of the inputs, just their shapes and their data types. Good. Next up, I wanted to talk about how to interface with this, fun method for generating this just-in-time compiled code. And the key here, the terminology in JAX is primitives. In other frameworks, this would be called custom ops. And so that I've been using that term occasionally. But in JAX, the key point is primitives. And there's a really nice tutorial, which is quite dense. So it takes a few reads, but there's lots of really good information in this tutorial. And so this is in the JAX documentation. So this is a key one to look at. And so the things I wanted to highlight are that if in practice, what you need to do is a primitive is just, it's some collection of functions that know how to do various things. And for our purposes, the things that your primitive needs to implement are an abstract evaluation function and an XLA translation function. And then the last one is for differentiation. And like I said, I'm not going to talk about that in too much detail. So, but that's the other piece that's required for a primitive. So the abstract evaluation function, it tells JAX what shapes you would expect as output, what shapes and data types you would expect as output, given some set of shapes and data types for your inputs. And then the XLA translation tells you actually how to connect this to a C++ implementation or a CUDA implementation in the background. And so those are the two key things. And so I'm not going to show an abstract evaluation rule here, I don't think, but we can look at those later. But I did want to show a translation rule, and essentially for the kinds of things that we're talking about today, what you're going to do is you're going to have this custom call. You're going to return this custom call object, which is a description of how to evaluate your operation using XLA. And this comes with specifications of the input and output shapes, and then the name of the operation, of the custom operation in the back end. And then the way that this corresponds to C++ is through a CPython module, which in the tutorial I implement using PyBind 11. But a key point is that it's just a standard CPython module. So that means that it doesn't have to be. You could write it in CPython, or you could write it in using the C API, or you could use Swig, or you could use Python, or any way that you're comfortable writing Python modules. You can expose these operations through that. And so that was sort of like a key realization that wasn't really, it wasn't like obvious anywhere that was true. And so that was one of the things that I learned when trying to learn how to do something like this, is that I could translate everything that I'd learned about building Python modules to exposing custom primitives to JAX. And then finally, this is what the actual C code looks like. And you're just handed a set of pointers that there's some like rigmarole to like get them in the right types and that kind of stuff. But at the end of the day, you're just handed these pointers and you do with them as you see fit. And so if you have some code that works on an array of doubles or floats or whatever, then you're done. This is what it looks like. And so the takeaway here is that there's quite a lot of boilerplate, and that's what I try to explain in this. Yeah, Kyle likes that void double star. The worst one actually is if you look at the outputs here, they're passing in a void star, which we're then interpreting as a list of void stars. It's really horrible. So anyways, that's life. Okay, broadcasting into the void. And so yeah, so I was saying there's a lot of boilerplate, but in fact, it's like once you've sort of got the infrastructure figured out, it boils down to like a pretty familiar set of operations, and so there's some and so that's like the key realization, is that you once you've got the boilerplate, it's probably not too hard. Good. So there's a question in the chat about if the arrays are assumed to be dense, and how are multidimensional objects passed. And so I'll say a few things about that. So essentially, there's no assumption about the structure of you're handed these void stars, and you interpret that memory however you want. And so there is some, there's some like safety concerns or whatever. There's one thing that you do is in here, the shapes inside of your Python, the shape objects that you're passing actually specify strides and stuff like that, and the order of the axes and those kinds of things. So in particular, I would require C contiguous multi-dimensional arrays, and then they're passed in as they would be passed in as a flat double star pointer. And then what you can do is, in fact, so here I'm not passing in any details about the dimensions of the problem. So, but in fact, you would want to pass in the size. And so the way that you would do that is you would actually pass in like an int or something like that as your first argument, or a list of ints or something like that. So you have to provide that information yourself, but this is pretty flexible about how you do that. And so I can show a more specific example in the code later. But essentially, sort of, the details of the assumptions that you make about the memory structure are up to you. And there's a set of rules for how you coordinate that between the Python and the XLA. Great.
Sorry, on the last slide.
Yep.
Yep. Sorry, the translation at this point is not referring. Do you even make reference to the backend function you're going to be calling here?
Right. Yeah. So here you see I have this string that says name of the op.
Yeah.
So that's the thing. And so for example, here, this is my PyBind 11. And so CPU Kepler _ F32 would be name of the op.
Oh, yeah. Oh, no, I see it now. Yeah. Okay.
So that's the connection. So it's passed as a byte string. That's how you tell it what C function is being called.
Okay. Thank you.
Yeah. Good. Any other questions? Good. So, oh yeah, and then the last thing I was going to say is it has been so like all of these different libraries have very different approaches to how they let you build these extensions. And for example, like building custom ops for TensorFlow is an absolute nightmare. I have done it a handful of times, but like, you know, talk about boilerplate and sort of it's anyways, that's crazy. And then Theano has this insane way where it actually, you implement the C code as strings in your Python, and then it like at runtime generates a C file and then compiles it in the background. It's just, you know, so and so that is actually awesome, but like really hard to support, you know, large user bases. And so it's nice the way JAX does it, and in that it's just this, there's just a C Python module that you can interface with, and so so you can distribute binaries on as like binary wheels, or you can put it on Conda, and you know, things will just work as far as I can tell. I'm sure that there are edge cases where that's not true, but so far so good in my experience. And so yeah, so this is that's the thing. Okay, so from here I wanted to switch to actually looking at some code and chatting in more detail. But perhaps now would also be a good time to see if there are any sort of high-level questions or anything like that that people might have.
Yeah, I think all of us would be very interested in seeing code, but yeah, if people can raise their hands if they have questions right now. Kyle, go ahead.
I was just curious if you have if there's like in terms of like CPU, GPU stuff at the high level, do you register somewhere in there that there might be multiple backends?
Yeah, great. Let's talk about that once we're looking at the code. Let's talk about that a little bit more, because it's a little finicky, and the way that I do it is not amazing, but I haven't come up with a better way.
Okay. Yeah.
And then I think the next hand we had was from Vengels.
Hello from me. I have a question. I will try to express it nicely, but I'm also not very expert on these things. I'm very new, so let's see how this goes. So at some point you saw the function, how you define the function, and you compile this with JIT. And you told us that because in the beginning you don't pass values, you don't want to have any conditional that depends on these values. And this is because you're going to compile all the graph together and send this, offload this to the GPU, let's say, with JIT. So I'm wondering if one will to pay the price of the computational time in order to use conditionals that JAX will pass dynamically to the GPU. Does it make sense?
Yeah. So a few things to say. So first of all, it's totally fine to have conditionals and control flow in your C code. I mean, like by the time you're calling the C code, you have concrete values. And so everything is, so that's all fine there. And that can, like, so some of the places where I'm using this kind of technology, it's actually because there's complicated logic in the back end, and that's exactly why I want to use something like this. Now, I'm not sure if is that sort of like, I'm not sure if that answers your question. So there are some like high level control flow operators in JAX. So there's a conditional function or a switch function and things like that, as well as an experimental loops interface. And in practice, some of those can get good performance, and some of them don't, and it depends on the details of your particular problem. And so I'm not sure that I know sort of, you know, I think it's not entirely obvious which is, you know, when one will be better than the other.
Okay, I think that the second part of your question, of your reply, answers my question. The first one is also, I understand what you talk about, that when you pass your C++ routines on the back end, there you can have whatever you want because you go away from Python. And just, okay, yeah, thank you. Thank you.
Yeah, good.
Okay, and then we have one more question from William. And I think we have another question in chat, but let's do William's first.
Great.
Sure. So first part of the question is, so I'm seeing here that, or I'm assuming that you need to pass, or also to your system, the custom derivative for whatever operation is you want to do, and so on for other variants of the derivative. Have you considered using a tool like Enzyme, which is able to embed the derivatives into, say, PyTorch and TensorFlow, not JAX, and create them automatically? So then you could say, inside of your system for JAX, not have to have the user create a custom derivative for the operation they want to write.
Good. So, so we can talk more about the specifics of that in a minute when we're looking at code. But I guess sort of I'm not very familiar with that particular tool that you're talking about. JAX does take a somewhat different approach to how it defines derivatives than TensorFlow and PyTorch, in particular related to like how they handle higher order derivatives, which is related to the question in the chat. And so in fact, so there can be some issues if all you know how to do is compute your first derivatives in C++, which is the case for some of the projects that I work on. That doesn't necessarily play nicely with JAX. And so, so I think it's hard in general if you're writing custom ops in C++ to like automate the process of generating derivatives, even with existing like source to source translation and stuff like that. But I'm happy to sort of delve into the details a little bit more if we have time later.
Sure. Okay, in which case then the second half of the question, which one we should definitely talk about that a little more offline. But the second half of the question is there any specific things you need to do with respect to memory management from CPU to GPU, just because there's typically different address spaces from GPU and CPU address space? And I can imagine you might want to have a custom op that, say, mixes CPU and GPU data. Or do you just need to cleanly say at the Python to C interface, this is where, you know, everything else has to live on one device?
Yeah, good. So I basically have no idea how to answer that. I think so. I like learned about CUDA programming like a few weeks ago, so I'm like super. I'm not sure that I'm going to be able to be very useful on the technical details there. I know that the way that it works is it uses like CUDA streams and stuff like that to try to, you know, stay on the GPU as much as possible. And I did not, I just like followed example code to like implement my GPU ops, but I'm sure there's sort of better, smarter things you can do in terms of memory management.
Okay.
So that's like way above my pay grade. But I again, I would love to know if people discover more things. I'd love to hear.
Oh yeah, for sure. And also, yeah, happy to talk offline as well.
Great. Yeah, sounds good. I was just gonna, so there was a question in the chat here that I wanted to comment on. So the question is, how does using custom ops make it not possible to get higher order derivatives? So that's one of the things that JAX does, is it can take arbitrary ordered derivatives, and and it depends on how you implement your derivatives. And so like I was saying before, if you have a custom op that implements the derivatives, then it can be tricky to make that play nicely with JAX. But a lot of the time, it turns out you can actually write your derivative rules as sets of existing primitives. And in that case, it'll do just fine. It can differentiate through that. And so for example, the Kepler example in the blog post, that supports arbitrary order differentiation. And so it's not like a fundamental limitation, but it does depend on the details of how you implement those derivatives. Good. And so then Kyle also has a question about derivatives. And again, so far I haven't made any reference to that. And again, in this particular example, the C++ doesn't ever say anything about the derivatives. And that's because I can write the derivatives using implicit differentiation just as a function of the result of my op and sort of standard other ops like derivatives and trigonometric functions. There's another hand up.
Yeah, so we have one more question, and then let's, after we take Vasil's question, let's maybe just to make sure that we have enough time with Dan, let's go to code examples. Then if there's time afterwards, we can take any more.
Great.
So yeah, Vasil.
Okay, thanks. Very nice. Thank you for the presentation. I wanted to ask you on the CUDA node. So can you describe a little bit the computational problem that you have? For example, I wanted to follow up on Billy's question first, but so normally when you want to mix CPU and GPU, it's because that the problem that you're solving has a lot of control flow and it's not canonically parallelizable. So do you have such use cases, or it's more like something that can straightly map to a highly parallel architecture?
Yeah, I'm not sure that so in this particular example, the parallelization is straightforward, and implementing the op on the GPU is simple. And so in fact, I'm not doing any switching. So it's just, if you're running in a GPU environment, it would use the GPU, and if you're running on a CPU, it would use the CPU. As the user, you can choose to position your whole op on the CPU or the GPU, but I'm not sure. I actually don't know very much about how JAX would handle or mixed ops. And so I'm not sure that I can provide a very satisfying answer to that. But I do have some places in my work where I have code that only runs on the CPU because of those reasons that you were talking about, and I haven't been able to figure out how to make everything work nicely together yet. So all that to say, sorry.
Yeah, I'm super happy to hear that you have a problem that maps to a GPU. Lucky you.
Yeah. Yeah, I've been spending a lot of time trying to figure out how to rewrite some of my algorithms as associative scans and stuff like that. So I'd be happy to chat about those things offline. Good. Okay. So I think so I was going to show, just sort of talk through this repo to like point people in the direction. I think, oops, I think it's sharing my wrong screen. Desktop 2, yes, please. Do you guys see code or slides?
We see your GitHub repo. Okay,
perfect. You'd think after all this time I would know how to use Zoom, but apparently not.
I still don't also. So.
Good. Okay. So I wanted to just quickly talk through how the pieces fit together. So So first of all, I was going to say, so this is the blog post repo that I was talking about here, and you can see that there's an outrageous amount of text here. So if you want details, this is everything that I know written here. But I wanted to point out some of the key bits here. So first, good. So first, all the Python is implemented in this Kepler JAX module here, and to register your ops to register your XLA implementations with JAX is as simple as this. You import your CPython module, which I keep emphasizing is how everything is implemented, and then you connect a byte string, like giving the name of that op, with the Python capsule, which we can talk about in a second. But this is all it takes to connect to tell JAX to know about that particular XLA operation, which is cool. And then here's an example of an abstract evaluation function, which I said maps input types and shapes to output types and shapes. It's particularly simple in my use case here, but that can sort of show you what's going on. And then this is the full implementation of the XLA translation rule, and this is I think Kyle asked about specifying the backend. And so here I have this conditional that where I'm registering translation rules for the GPU and the CPU separately. I haven't figured out how to do this in a cleaner way, so I actually just register the two separately, even though lots of the logic is the same. But yeah, so here I would, this is, the name would be CPU underscore Kepler, and here the name would be GPU underscore Kepler. And so that's the main difference. The only other difference is here, I mentioned that you need to pass the dimensions of the problem. And so here I'm passing an argument on the CPU, I'm passing an int64, which is just the number, the size of my arrays. And then on the GPU, I'm not passing that. And this has to do with things that I'm sure y'all know more about memory management and transfer and stuff like that. But in fact, I'm passing it as this opaque object. And it's annoying that you can't actually use opaque on the CPU as well. It would be nice if there was a consistent way of doing it, but for some reason there isn't. And so anyways, all that to say that's why the syntax is slightly different between these two. Lucas has a question, I think.
Yeah, I mean, it's a more general question, but touches on this platform dependence. So I guess, I mean, there are multiple ways to kind of extend like the full stack. So you could like write, like a custom Python function, write, like derivative rules for that. Mm-hmm. So what you're talking about is you're extending JAX like on the C++ level. I think there's like one more level below that you like add new XLA ops.
Right. Yeah.
And I guess at that point it's similar to adding new ops to TensorFlow because that's, I think, shared code. And so can you compare and contrast kind of the effort needed for both of them? Because I guess if you have a new XLA op, at that point it's kind of native on TPU and GPU, and you don't need to do all of that work.
Yeah. Okay. So a few thoughts about that. So first of all, I think you say native on GPU, TPU. Right. But I mean, I think that would involve actually writing all the code for all of those platforms. Right. I don't think it just comes naturally, right? You would still have to provide implementations on all of those platforms. So I think, and then from a user perspective, it would be a pain because they would have to recompile JAX lib, probably. And so you would have to either get it merged upstream or have someone like install your forked version of JAX that has support for that custom XLA op. So I think unless you have something that's really fundamental, where it might be worth pushing it upstream, I think something like this is about the same amount of work.
Okay, cool, thanks.
But yeah, you're right that it would be possible to do that, but it would involve sort of buying into the TensorFlow ecosystem and figuring out how to contribute to that, which might be worth it, depending on what you're doing. Great. Any other questions? Cool. Okay, so then the last thing I wanted to show in here, I don't know, should we, what's our timing like? I guess officially we've hit an hour, so.
I think our timing is more really whatever your time is, because I think people can hang on or drop off as needed, but I guess it's kind of more how long do you want to go for?
Okay, sure. Yeah, I mean, I'm happy to chat a little bit longer, and there were a few other things I wanted to show quickly, but of course, feel free to drop off and that kind of stuff if you know, since we're over time.
And as a reminder, this will all be recorded and put up on YouTube. So if you have to leave early, you can always catch it later.
Awesome. That's embarrassing. Okay, so so the last thing I wanted to show while we were in Python here, and again, I'm not going to go into too many details, but there's this question about how do you provide support for derivatives, and so in this particular case, the way that I can compute derivatives is I can use implicit differentiation on this and rearrange things in order to evaluate those derivatives given some value of the input. And so actually it's pretty clean how this works. And so this is my entire implementation of the derivatives, and this will support higher order differentiation and all of that kind of stuff. So this is it, which is pretty cool. In cases where your function is more complicated and it doesn't work out this nicely, it can be trickier, and there's more discussion in that tutorial, the How JAX Primitives Work tutorial, about how to support you know, more complicated things. And then I would just point to, so I have this project, Celerity.
Will you say, and that's the code for actually calculating the derivative, but in terms of like how you sort of register that with the.
Okay. Yeah. So again, this isn't the code to calculate the derivative. This is the code to trace the derivative. This will never be called with concrete values.
Okay, sorry. Yeah.
But yes, your point is good. So this is how you register everything, and so in particular, the way that you register that function is as follows. There's this dictionary, and you just provide a function for your primitive on that dictionary, and that's it.
Okay, cool. Thank you.
Yeah. This is all the boilerplate that you would need for registering all of these functions. That's a good point. But what I was
when you get the, sorry, can I ask on that code there where it said core.primitive Kepler or something? Yeah. So that's the same name as the kind of primitive that you created in the first place. That's somewhere up there. Is that right?
This name has no relation to the XLA names, that it can be different. This is just this is like the name, the like, I think you just can't have collisions. So like you wouldn't want to call this exp, I think.
Right. No, but I mean, like, how do you know, where do you tie that the derivative related stuff to like the forward, like the normal evaluation of the function to say it's like the same thing?
Okay. Yeah. Good. So at the top, this is the only public facing function in this module. And so users would call this function, and in this function, I bind that primitive.
Okay, that's great. Thank you.
Yeah, good. Yeah, there's sort of lots of pieces, and it's not very well documented. So, so yeah, thanks for bringing that up.
Yeah, sure. Thanks.
Good. So, oh yeah. So I was going to say, if you only know how to evaluate your derivatives in C++, which is the state that I am in this project, at least for now. I do have example code here for how to hack the system, and this doesn't support higher order differentiation, but this if you're trying to translate something like an existing op in Theano or TensorFlow, this might be more similar to how you would easily translate it. And a lot of the stuff that I do, actually, it wouldn't be that helpful to have higher order derivatives. So it's maybe okay, but that's not today's discussion. Good. And then and so then I just wanted to point to a few other things. So the actual implementation is in this directory here. And a lot of this is boilerplate. So the kernel helpers and the PyBind 11 kernel helpers, those kinds of things are essentially just taken from the JAX lib implementation, so in the JAX repository, but they don't expose it in a way that's easy to copy over. So so that's boilerplate, and then these files just have these voids all the way down functions in here, so you can see how they're implemented. And my CUDA kernel is absolutely trivial, partly because I don't know what I'm doing, like I said before. But that's how you would look at how they're implemented. And then the last thing I wanted to say is just to emphasize one more time, this is just a it's just a standard Python extension module, and same with the CUDA one. Although I have some extra functions above here for compiling the CUDA code using CMake. You can use, like, if you have an existing method for exposing CUDA code in your Python module, you definitely don't have to use CMake. It would be possible to do something like this using a different, like, writing it directly in setup tools or something like that. But I found it easiest when I was developing this to use CMake for that. But otherwise, the setup.py is pretty similar to something that would be familiar. Good, and so that's sort of the last of the tour that I wanted to give here. Are there sort of any last questions? Any things people wanted to chat about some more here? Things I missed?
So I'll, in in the interim between maybe other people thinking of questions, I'll kind of ask maybe just kind of a more philosophical or one to some degree. So here, and also in your very nice GitHub repo, you've shown kind of a path forward to actually doing this, but do you have any kind of general recommendations or comments on what to avoid, or what were things that you hit while first doing this that you'd like to kind of point out in the kind of here be dragon sort of way?
Yeah, that's a good question.
I ask mainly because I think a lot of us are going to go try and do this with our own kind of like toy examples, or start to try and see how we can extend things as well.
Yeah, I'm not certain that I do have, like, I mean, I think the big thing is that it is there is this problem that if you're writing a custom op, you also need to provide the derivative somehow. and the issue that I've sort of been like spinning, especially on this Celerite project. Ever since I started working with JAX, I've been like trying to come up with like clever ways to parallelize it and generalize the derivatives and all of these kinds of things. And I think, and I do get better performance by providing these custom ops, but maybe not drastically better performance than I would get if I directly implemented it using the JAX scan or something like that. And so I think there are some questions about like, if you're going to be putting in a huge amount of time, like thinking about these things, it's, you should be doing it for the love of it and not necessarily because it's going to make your life easier. But I do think so. But like a lot of my time was wasted on like figuring out like reverse engineering the undocumented APIs and stuff like that. And so I do think that it's at a point where it is worth trying this for your problems. And in fact, you can probably copy and paste a lot of the boilerplate that I have here and get some results pretty fast, which lets you benchmark and like figure out whether or not it's actually a good idea. And so I think it's you should definitely go try it and tell me what you learn. Open issues on this blog post or something when you discover all the things that I'm saying that are wrong. And yeah, I'd love to hear.
Okay, great. Okay, well, I don't see any additional hands raised. So unless there's any very final questions, Dan, thank you so much. I know I definitely learned some things here, and I bet everyone else did as well. So we really appreciate you coming and giving this talk. Thank you.
Amazing. Thank you so much for having me. And I'd love to chat offline if people have more ideas or questions there.
Sounds great.
All right. Thank you again, Dan.
All right. See y'all later.
Yeah.
Cheers.
Take care. Good luck.
All right. Bye.